Okay, let's go ahead and get started, and a few more people will trickle in as they come. Uh, Good morning or good afternoon, everyone. It's my pleasure to introduce our guest speaker today, Noah Smith, who is the Vice Provost for Artificial Intelligence and the Chair for Artificial Intelligence and Emerging Technologies at the University of Washington. He's a Senior Director of NLP Research at the Allen Institute for Artificial Intelligence and leads the NSF and NVIDIA-supported project Open Multimodal AI Infrastructure to Accelerate Science. Today, he'll talk to us about Olmo, Molmo, and open multimodal AI infrastructure to accelerate science. So without further ado, I'll hand it over to Noah. Thank you for being here.
Thanks so much. Thanks for the invitation, and I'm delighted to share with you today. Can you just want to make sure you can hear me? Sound is good?
Sound is good, and
Okay.
screen sharing is good.
Awesome. Okay, let's go. My top level message today is I want to expand the way that you think about AI. AI is a field with a long and rich history going back some 70 years. And only recently did it become, a major commercial presence and technological presence in our lives. When we think about AI today, we think about chatbots like Claude and ChatGPT and Gemini. We think about agents. We think, if we're a little bit technical, we think about APIs. But I want to put forward that, particularly when we come to this new technology as scientists, we should demand more. And I think, scientists have a long history of investing a lot of time and energy in building their own tools and their own instruments and apparatuses to help them do their work. And it's deeply important that we understand and control those technologies. And AI is becoming one of those technologies. So my position for some years now has been that if we're going to build AI that serves scientists, then we need to think of it as infrastructure, and we need to think of it. We need to develop the technology itself in a way that allows inspection and control by scientists. The way we think about this at the Allen Institute for AI, or AI2, where I spend about half of my time, is this concept of a model flow. So model flow is a collection of artifacts that provide you a rich amount of information about the full design and creation of an AI system. So for today, for language model-based AI, this means we have all of the training data for every stage of training, model weights, not just at the end of training, which is a useful artifact that many labs are sharing, but actually model weights all along the way at every step along the training process, the intermediate checkpoints of those weights. Details of the recipes used to train the models, including algorithms and data, code to reproduce those training runs, fully open evaluations that detail every measurement that we take along the way, and documentation, technical reports that detail what we've done and analyze the process. We refer to this as full openness, everything that you would need to do reproducible research. So we really think about two kinds of beneficiaries of building model flows. One is the scientific community, who, as I said before, is increasingly turning to AI systems as tools for research, instruments for research. The other is the AI research community itself, which benefits tremendously from being able to poke inside and see every part of this process and do interventions and controlled experiments, as scientists want to do, to learn more about AI and advance AI research. So I'm going to point to Olmo 3, our release, our big full model flow release from end of last year as an example. You can read the tech report. The QR code there should work. What we released with Olmo 3 was the full model flow. So we have checkpoints along every stage of training. We had multiple branches. It's actually not just one model. It's three different models tuned for different purposes, different behaviors. One focusing on instruction following, one focused on thinking or reasoning is the word we use mostly now. Another designed for reinforcement learning research. You can interact with these models at the link on the slide. We're not building these models to create customer experiences the way that the frontier labs are doing. We're building them to support research and support scientific advance. But you can interact with them, and they're quite good for their size. We build models at the 32B and 7B scale. This is sort of an aggregate plot of performance metrics across two different suites, one for base models, one for adapted models, and comparing to other open models. And so what I want you to see first is that compared to other offerings at the same time, like Qwen 3, this is a very, very strong, competitive open model, but also that we're the only team releasing the full flow, where you can see the performance at every step along the way, from the end of from the end of pre-training all the way up through the end of reinforcement learning. So again, full model flow. You can use this in ways that you can't use a final model that's only open weight. I also want to point out, this is, I could talk a lot more about these details, but we're a very small organization. We're a nonprofit. We don't have a revenue stream. We're philanthropically funded and funded now with support from the National Science Foundation. Our goal is to optimize the quality for the costs that we pay, because we have a very limited budget. We have a very small team relative to the Frontier Labs. So I'm really proud of these facts. Our data budget is about 1/6 of what Qwen 3 was using to train, and we're also using, compared to Llama 3, which is another important model from a year or two back, we use about 40% compute per token. So there's a number of metrics on which we just do really well on efficiency, and this is a big part of our research agenda. Is one, to make training these models less expensive so more people can participate. But two, also, I'm always amazed by how much stronger the slightly smaller models are doing compared to the bigger ones of a year or two ago. So building at the 7B scale or other smaller scales, I think is there's still a lot of room for improvement, and I think we will be surprised in the coming years about what smaller models can do. So this effort, Olmo 3, came out in, I think, November of 2025. It was obviously the third in the series. We started this work in early 2023 as a response to the closing down of details and information by OpenAI when they released ChatGPT, and it really went commercial. Our team's response to that was we were frustrated. We want to participate in cutting edge AI research, and we didn't think that you should have to work in one of the frontier labs to do that. Starting around the middle of that year, 2023, we started making the case to the National Science Foundation that building these fully open model flows, we didn't use that term at the time, but building fully open AI systems was a kind of infrastructure for science. And really delighted in August of last year, almost a year ago, the award came through with support both from the NSF and from NVIDIA. So we internally, we refer to our project as OMAI. It's easier to say. But OMAI is the NSF mid-scale research infrastructure project supporting the Olmo models and all the artifacts around them. As the project got underway over the past year, we figured one of the things that we were in a good position to do, and that just made good sense, was to talk to scientists outside of our own research collaboration networks and find out, what do they want from AI. You can take the survey. The QR code is on your screen now. We're still collecting responses. I think we have more than 600 so far. And some very clear themes have been coming across in the answers. And we're getting a very diverse set of scientists responding from across many fields and different career stages. There are two things that I think bring all scientists together. Okay, the first one is data. Scientists want AI to support data processing, parsing and managing different kinds of data, multimodal data, image data, integrating different kinds of data, dealing with large, high-dimensional tabular data. Everybody's got specialized kinds of data and contextual interpretation, and they want AI to support the work that they need to do with their data. This is completely unsurprising. This is what we anticipated when we wrote the proposal. The other thing that scientists all share is not just literature, but an overwhelming amount of literature. I think we all have this sense in recent years that the amount to read has just exploded. Doing literature review is getting harder. Staying current on your field is harder and harder. There's also stuff outside your literature. There's other stuff you need to read that relates to bureaucracy in your organization and with your funding agencies. Basically, this kind of literature and related document management is a huge part of our lives, and this is where AI really does shine, or could shine, I think, if trained appropriately for the kind of careful reasoning and nuance that we need in scientific work. So the two parts, the two foundations, I think that bring all scientists together: data and literature. And these are the two kinds of things that are going to drive through the OMAI project. We have a wide portfolio of research and development across the whole model flow, and what I'm going to focus on with the rest of this talk today is recent research projects that are informed by and motivated by the needs of scientists, but also, I think, occupying an unusual place in the ecosystem of AI research itself. So I'm going to spend a little time on 5 different projects. I'll give pointers to the papers if you want to read more deeply. I think in the past when I've given this talk, it lasted maybe 45 minutes, so we should have plenty of time for questions. I've got a couple of videos in here that are more visually engaging than anything I could make. So I'll just say, yeah, let's dive in, and we'll get there in a minute. So I want to talk first about our multimodal models. So our first multimodal model was called Molmo, for multimodal Olmo, and Olmo stands for Open Language Model. It's not a very creative name, but it's stuck. This work earned an honorable mention for best paper at CVPR last year. And the point of the paper is basically that if you're going to do multimodal AI, you need open data. And that includes really, really high quality, detailed, human-generated captions of images and instruction data for image tasks and pointing. The Molmo paper really introduced this idea of pointing to localized visual evidence. And this has been really exciting for our colleagues who work on agents and with robots and systems that interact with the web that need to act. I'm not going to focus on the action stuff so much. I do want to emphasize this exciting kind of development around having models simply point within an image. What you see here is tracking across a number of different multimodal models the quality of the pointing performance. Before Molmo was released, this was just not something people were really doing. It wasn't a real central task in the suite of evaluations. After Molmo, that changes, and it actually took some time before leading labs like Google were catching up to what Molmo could do in terms of pointing. We earlier this year released Molmo 2, which expands to video and does more in the space of grounding. So it supports single images, but also multi-image inputs, video, and it can do pointing and object tracking, and it gives grounded chains of thought for certain kinds of tasks. Possibly more important than the model itself are the data sets that were released for training this model. 9 new data sets, including video pointing and tracking, dense video captioning, long-form QA, and lots more. And there's, I think this is a point of contention within our team. Is it important that we not distill from proprietary models? I think at this point in our team's history, it was a point of pride that we didn't do any distillation here. I actually think personally distillation is not an unreasonable operation. I think one of the best uses of generative AI is building extremely high quality data sets for focused problems that can help you build the next generation of models. That has to be done with care. But in any case, Molmo 2 didn't require any distillation. I'm going to play a video about Molmo 2 that our communications team made for its release. It's just way better than anything I can present. And I'm just going to say, I know this looks like advertising, but we're not selling anything here. We're a nonprofit. All of this is free for you to download and use with very friendly licensing. So here's the video. Oh, where's the sound? Okay, hold on. We need the sound. There we go.
The next generation of Molmo is here. The original Molmo charted new territory in image understanding. Now we bring that same multimodal intelligence to the dynamic world of video. Molmo can now count and track objects or actions in a video, as well as answer complex questions. Molmo, what did the white team do wrong here?
The white team failed to clear the ball effectively. When the blue team attacked, they managed...
Molmo doesn't generate videos. It helps us to understand them. Molmo, can you create step-by-step instructions from this cooking video?
Here are your step-by-step instructions based on the clip.
Molmo 2 is trained on the largest fully open video-centric multimodal corpus to date, combining the fluid intelligence of an LLM with the spatial awareness of an image encoder. Molmo, why can't the cat get the snail?
The cat can't get the snail because there's a glass window between them.
Molmo's artifact detection can even help locate anomalies in videos that may be generated artificially.
Artifact detected.
Molmo can reason across multiple images, documents, or videos simultaneously. With the ability to reason across multiple live input streams, the possibilities are endless. Molmo is available now, completely open for researchers and builders to inspect, evaluate, and customize.
Yeah, so
the next generation of Molmo.
I didn't want to play it again. All right. There we go. Yeah, so we're obviously really excited about this work, and we've been continuing, not to get too much into the technical weeds, but there's already been a number of follow-on work. So we have a new paper out called Molmo Point, which gets into the way that the pointing works. So just a little bit of technical flavor here. The way that Molmo originally generated those little pink dots in the image was text coordinate generation. It was literally using the language model to produce the numerical coordinates as text. Which, if you like me are the kind of AI researcher who believes we should respect the data and represent it in its native form, this is weird. Like, really, the text coordinates should be grounded in the image. They shouldn't just be generated as language. So Molmo Point replaces that kind of generation with what we call grounding tokens that directly select the visual tokens from the input and then refine them to subpatch and locate. So this is a more natural control surface for dealing with things like text coordinates, and this has been important in our work going forward. So you can kind of think of it as like taking each little piece of the image and having little heat maps that decide where is the right brake light or the leftmost car across this image, and localized by actually looking at the pieces of the image, and then the pink dot follows naturally from that energy function. And so this leads to better and more efficient grounding compared to Molmo 2 and other systems. It's also way more data efficient, so we're able to learn to do pointing with a lot less data and get higher performance faster using this technique. So I think this is a beautiful example of building your model with better inductive bias for the problem you're trying to solve. Where we're headed next with multimodal, I think is really exciting and very much motivated by the scientist user community that we're building. Grounding is essential for these examples will hopefully make it clear for scientific settings where you really need to check the answers the AI is giving against the evidence. So things like counting, measurement, you can see these are medical images, longitudinal comparison, very important in medical imaging. These are the kinds of images that we are working on training on now. So we sort of have two multimodal projects at the moment that are noteworthy. One is pushing towards 3D spatial reasoning, and the other is focusing on particularly medical and biomedical images. And we're using a lot of creative data sources like textbooks to help us with this. But the idea is to really push the models to be especially useful for the kinds of imaging that come up in biological research. Okay, so now I want to pivot to something more text focused. I'm a language person. I think the literature side of of research has long been an inspiration for me in thinking about how AI can help us. And so I want to talk about the DR Tulu project, or I call it Dr. Tulu. You can see a demo of this. This is our fully open deep research pipeline. So this is an end-to-end recipe that helps understand how we build these long-form deep research agents that carry out the kinds of tasks that, like literature review, that require search and understanding and synthesis from literature. So the agent stack includes search and browsing tools, asynchronous tool use, MCP-based infrastructure, and there's an evaluation suite to help drive the field forward and help others make contributions to make this stuff better. I'm going to show a video so you can kind of see. It's a very transparent deep research system. It tells you what it's doing all along the way, and you can inspect every step and see how the evidence is integrated. We have a little demo video. There's a technical piece too. I'll save that for a minute. Here's the video. There's no sound, so I'll just sort of make notes as we go. So we're asking a question about detecting road surface cracks automatically. It starts with planning. This is standard thinking, but we're showing the user what the thinking is. It decides to use Google search. It's looking for surveys. It's getting the results. It's going to do some more reasoning. It's found some reviews. It notes what it still needs to go find. So now it's going to go do some web browsing and look at one of the websites and evaluate the latest models. Now it's understood more of the models that are being used, but it still needs to go find metrics. And for this, it's going to do a paper search across our collection of papers on the specific topic. And now it's reflecting, it's going to do some more thinking, and then finally generate an answer, which is this, multi-paragraph long form response, like your research assistant could maybe write for you. But it's got citations, and you can go follow those and check back and validate. So very, very important, I think. All right, how do we move forward? One of the cool things technically in this work that I want to point to, this idea of using rubrics to judge the quality of language model output has become very popular. Many tasks have sort of multifaceted, complex evaluations that you need to perform if you want to understand how well the system's working. It's not a simple right or wrong answer, right? Like a lot of things that we like to evaluate in AI, or like games where you just you evaluate whether you won the game. So rubrics are with language models. They're a really beautiful way to solve this problem. You use a language model as a judge, give it a rubric, and it can evaluate an output from another model along many dimensions. What's interesting in the DR Tulu work is that the rubrics are actually evolved along with the policies. So we're actually developing, improving, evolving rubrics through the learning process to drive the system toward better responses. I think this is a really nice example of we're building a real system. We're building artifacts that people can use to build even better systems. But as we carry out that artifact building work, we're also doing basic research and making new advances in the technology itself. And I said earlier, we're always trying to optimize the quality over the cost. And I think with DR Tulu, we have a really great success story. This is the cost of doing inference, of running the models. And you see DR Tulu is a whole lot cheaper, but it's matching the performance across a suite of benchmarks of OpenAI and Claude and other systems that are far more expensive to run. Okay, my next point continues on this efficiency point. Because we're building models from scratch and getting all the way into the deepest, most technical details of how these models work, we're also able to experiment with new ideas that are really at the cutting edge of model architectures. So this is new work called Olmo Hybrid. It'll be a paper at the Conference on Language Modeling happening in San Francisco in October. Really exciting results. This is a beautiful piece of work that ties together both some elegant theoretical results with really practical ones. The technical idea is quite simple. If you know about transformers, you know that they are built out of sort of an alternating pattern of attention layers, which is a particular kind of neural network operator, and multi-layer perceptrons. And basically, the original transformer, alternates between these two kinds of layers. In Olmo 3, we use two different kinds of attention. One is called sliding window attention. We would have 3 layers of sliding window attention, and then 1 layer of what's called full attention, which is more expensive. And this worked pretty well. It followed other recipes. And so it's based, it's a pretty classical, modern take on a classical way of building transformers. What we do with Olmo Hybrid is we replace those sliding window attention layers with something else called gated delta net with negative eigenvalues. And I'm not going to go through what exactly that means or why it has negative eigenvalues. The point is that this is a particular kind of neural architecture recipe called a linear recurrent neural network. If you've been in AI for a few years, you may remember that recurrent neural networks, and particularly a model called the LSTM, were extremely widely used in natural language processing before the transformer. And they were pretty much abandoned because the transformer allows really, really good throughput of massive amounts of data to train at really large scales. But theoretically, we know some things about recurrent neural networks that were left on the table when we moved to transformers. And recent developments have allowed us to come up with variants of recurrent neural nets that can be trained with the heavy parallelism that we have in the transformer. So this is basically the culmination of a number of different research efforts that allow us to reconsider the recurrent neural net as a component in our modern architecture. So what's cool about this experiment is we changed only one thing, right? This is the way you're supposed to do science. We changed only those three layers in each block from sliding window attention to this linear RNN. And why? Well, we did it because of this fundamental theoretical result that transformers and linear RNNs are good at different things. The transformers with only attention excel at recall. They're really good at looking anywhere back earlier into the sequence, earlier into the conversation to find relevant information and bring it in. But they're really bad at state tracking. Transformers don't do well at things like reading a chess game or the series of moves in a chess game from beginning to end and remembering where each piece is at each point in the game. Linear RNNs are actually great at state tracking, but because they don't really have a memory, they struggle at recall. Or they have a finite memory is a better way to say it. So basically, the hybrid models are stacking the transformers, which are good at recall, and the linear RNNs, which are good at state tracking, and interleaving them. And so the paper includes a proof that if you do that, if you build a hybrid model this way, you get more expressive power in a very formal sense than either of those models would have on its own. And what we found when we trained the model was that it learned faster. So what you're seeing with this pink line is the hybrid model, same size, same everything, same data, just different architecture. It gets to the same level of performance on key benchmarks like MMLU with half the tokens, 49% fewer tokens. It has better scaling behavior. It basically gets better loss for less compute. And we found this was true across a wide range of performance measures. Here it is stacked up against the Olmo 3 base model at the same size on a range of different metrics, and it's essentially matching or beating. Notably, it was a lot easier to get this model to learn long context extension, which is where you take a model trained up to some window, trained to look at only a finite window of context to give its answers, and expand the length of that context by training on longer documents and making some subtle changes to the architecture. Olmo Hybrid was a lot more adaptable for long context than the original Olmo 3. Why would better expressive power lead to better scaling and more efficient learning? We did some analysis under some assumptions of current theory, a theory called the quantization model of scaling laws, and we proved that this is exactly what you should expect. If you have greater expressive power, you should scale better under these simple assumptions. So we think greater expressive power has benefits for scaling. I'm not a theoretician, and I'm always frustrated by, I think this happens in many fields, the way that theory struggles to keep up with practice, and theoretical results are really hard to translate into real gains. This is a rare example in computer science where theoretical analysis led us to a really good experiment, and we're now testing these hybrid models to make sure that they're really as robust as they need to be. And it's very likely that Olmo 4, our model planned for next year, will be hybrid. So watch this space for more. Okay, we're doing great on time. So the next thing I want to talk about turns to related to efficiency, is the energy use and environmental impact of language models. And this is work led by Jacob Morrison, who's my student at UW and also a member of the Olmo team, also appearing at the Colm conference. One of the arguments that we've made about building open model flows is understanding the actual costs of building these systems and operating these systems. A lot of the time, I think the cost matter, the environmental footprint really gets, we just don't have good information about what it costs to build really strong AI systems these days. We argue that in order to assess the costs, you have to think about the whole flow. You have to think about all the failed runs, all the experiments, all the ablation studies that you did along the way before you trained the final model. The DeepSeek model from about a year and a half ago got a lot of attention because it reported very low cost to train, and we were immediately frustrated by that interpretation because the report left out most of the cost. It focused only on the final run. So I'm going to just mention some of the key findings in this recent report based on the Olmo 3 work. It was really a follow-on of an analysis of what fell out from training our Olmo 3 32B model. Looking at the think variant, the reasoning model, post-training used about 17 times more data center energy than the instruction tune variant. And the driver was really the reinforcement learning rollouts. Water is an interesting thing that comes up a lot in these conversations, and we point out that water really depends on where and how the compute is powered and cooled, not just the workload. There's a huge amount of variation in data centers and how they work. And for Olmo 3, on-site cooling water was effectively zero. The quote we heard from the managers of the data center was that they use more water to mop the floors than they do to cool because they have closed-loop cooling. The water use that went into Olmo 3 came primarily from power generation. The other thing, this is maybe the most important point, development really dominates final runs. Olmo 3 development was 82.2% of the total GPU hours. Reporting only on the final run will underestimate the impact by about a factor of 5. By our calculations, but not just our calculations. There was also a report that came out a little bit later from Epic.ai, where they did an analysis and basically found exactly the same thing. Reporting only the final runs will understate the impact by about a factor of 5. And they looked at several different models for that analysis. So the take home here, I think, is that all of these different capabilities that we're putting into models now, the ability to reason or think or generate these chains of words, rambling, I like to call it, the use of agents and tools, these are control knobs and they have costs. And training a model to have these different capabilities is going to have different costs. Who should decide when the cost is worth it? Well, if these are scientific instruments, it should be scientists who are deciding how the model is customized and where we put the energy. I have one last technical piece, which is a new way to increase the amount of control that we have over how we specialize our models. So this is yet a third paper that will appear at the Colm conference, also led by Jacob, and the real senior driver of this is Sewon Min, our colleague at UC Berkeley, who's also at AI2. So We often think about these models as like a monolithic thing that gets trained and then you're done and now you have your new system. But really, we'd like to be able to update without having to go back and start from scratch. The cost of training a model from scratch is extremely high. Most groups can't do it. Um, and so what we'd like is to have a little bit more modularity in the way that we adapt models and improve them. So this work, we call our method branch, adapt, and route. The idea is quite simple. I'll go through it in a minute with visuals, but you basically are training separate domain experts, and you're adapting each one through completely separate independent stages that are appropriate to gain the capabilities that you want that expert to have. But then we compose them back together within a mixture of experts architecture and a little bit of lightweight router training. So the idea is to parallelize and make asynchronous the development of individual experts, but still allow their use in a single model. And part of making this work is to have an anchor expert that was initialized from the original model, and that expert is always maintained. So it never goes away, and specialization won't overwrite the base model's behaviors that were learned earlier. And I think that's one of the worries you always have if you say, oh, I'm going to download this model. It's already really good at a lot of things. I want to add one more capability. So I'm going to update the weights with this new data. There's always a chance that you're going to have forgetting of earlier capabilities when you do that. So this bar approach is intended to make upgrades cheap and local. So here's the visual. You have an initial model over on the left. And what you're going to, after you've trained that model, you're going to make copies. In this example, we have 3 different copies, green, blue, and red. I think that the symbols are meant to indicate the green one is for math, the blue one for code, and the red one for safety. And each one of these models is going to, we start with an initial model, but then when we make the copies, we're going to make them into mixtures of experts. Regardless of whether the original model was an MOE, these models are going to be MOEs. MOE means that you have copies of the feed-forward network parameters, and each token gets routed through one set of the feed-forward networks at each layer. It's becoming a very widely used architecture that has really nice computational scaling properties. But again, each of these 3 experts is now going to go through its own post-training pipeline. Or even earlier, math and code are going to update the mid-training and then do SFT and then reinforcement learning. The tool use and safety experts are only going to use SFT. Whatever data you have for the capabilities that you want to target, that's what you use. When you're done training each of these guys, you put them back together into a single MOE, and now it's you're really exploiting that mixture of experts by letting different experts be specialized for different capabilities. If you want to update the blue one later, you can do that, and you can swap it in. Each of the routers for these mixtures of experts was learned pairwise against the anchor, but they can be recombined to become a multi-way router across all the experts. So you don't have to retrain anything from the past. You can always add or swap in new experts, and so you get, if you want to keep adding experts as you go, you get linear scaling rather than quadratic. So this is the idea. We found that this worked really beautifully on benchmarks. So we have 19 benchmarks, and all the models are at the 7B scale. We were doing this work on the Olmo 2 base. Just to reiterate, when you release models fully openly, it enables research like this. So we were able to build on the team's earlier work. In any case, bar is the pink line. It's achieving almost the same performance as if we completely retrained the whole model for all the capabilities, which would be extremely expensive and undesirable. We're losing only a tiny bit of performance compared to that, and we're doing better than a whole bunch of different alternatives from the literature and that you could think of without doing the bar operation. And notably, at the very bottom, we have dense merging, which is basically keeping the same model size and not adding any experts at all. That fails catastrophically and gets terrible performance, worse than even the base model got across the suite. Okay, so popping up and wrapping up the talk, a lot of the time when we talk about the work that we're doing, people assume that what we're trying to do is just kind of an open version of what commercial AI companies are doing. And I think that would have value, but I think it's too small a goal. I think instead, what we need to think about is what are the needs of the scientific community that the market is not going to care about. Scientists need to inspect the system. They need to be able to make changes locally. They need to be able to study the development of the system. They need control. They need to be able to specialize it for really, really unique and problems and domains that are very unlikely to pop up on the radar of the tech companies that are really targeting a sort of median average user. So I think I'll just kind of reiterate that I think this open infrastructure, it's not something we're just going to build and hand off. We're trying to build what everyone needs to get them going so that ultimately I think scientists need to be building their own tools again, like they were before AI. And AI should just be part of that. So that's the open infrastructure we're working on within the OMAI effort, and I hope that you'll take the survey, sign up for the mailing list, engage with us, and build on the things that we're creating and share back. I'll close by acknowledging many collaborators and team members who were involved in this work. Their names showed up as authors on the papers, but also we've gotten various computational resources along the way from Microsoft, from the NAIR, an allocation on Frontier from Oak Ridge, Lambda, and then, of course, major support from NVIDIA and the National Science Foundation. Thank you so much for the invitation and your time, and I am really excited to hear your questions and have a conversation.
Hey, lovely. And we're right on the dot. So if y'all would join me in thanking our speaker, Noah, and thank you very much. We'll see you at the next webinar.
Thanks so much. Great meeting you all. Have a great day.
Thank you.